Okay, thanks. So I want to talk about, so I want to continue talking about optimal regularity. I want to broaden the perspective a little bit. But I want to begin with, well, first of all, I want to just recall where we were yesterday. So we're looking at two themes here, geometrically, and I won't really say anything about that. There will just be one or two slides here in the beginning, and then I'll leave that. But geometrically, we're talking about a sharp bound for the singularities. And analytically, we're talking about optimal regularity. So we talked about optimal regularity for this degenerate elliptic equation. And again, I want to broaden this a little bit towards the end of the talk. So again, this is all joint work with Whitney. So we're looking at the mean curvature flow. So again, this is where a hypersurface is evolving by this nonlinear differential equation, where the change in the position vector is minus the mean curvature and is moving normal to the hypersurface. Most of our discussion have been in the case where the initial hypersurface is mean convex, and again mean convexity is preserved. And again, it's known, it's well known that singularities are shrinking spheres or shrinking cylinders. And there's this earlier result of Brian White about the space-time dimension of the singular set using Almgren-Federer dimension reduction. And so the sharp bound, again, is a sharper bound for this. The examples of singularity that we have particularly look at, I'll talk about some other singularities in just a minute, but where by spheres, so we talk about singularities, and here we're talking about some simple rotational symmetric flows. So we talked about the round shrinking spheres, the round shrinking cylinders, and the Meritz ring. There was this rotational symmetric surface in our tree. And so in the case of the round sphere, it shrunk, became extinct at a point. In the case of the round shrinking cylinder, it shrunk to the axis of the cylinder. And in the case of the Meritz ring, it shrunk and became extinct in this simple closed curve. The singularities in all of these three cases happen at just a single time. And in the case of the dumbbell, this was a little bit different. The dumbbell we looked at, where the two bells was of equal size, there was three singular points and two singular times. Right? The three singular points were at the first singular time, the neck pinched off, and then there was two later singular points that happened at the same time. That was when each of the bells disappeared. So this optimal regularity in terms of the singular set. So this is what I talked about at the end yesterday. Again, all of these results hold in all dimensions. I just say it as if it was just in our tree, but they hold in all dimensions with obvious modification. Right, and so it's say that the singular set is containing this finite union of these compact C1 curves plus this countable set. Right, and so in particular you get this about the Hausdorff measure of the singular set, one-dimensional Hausdorff measure. And so even right, and in fact it's very sharp. It's very sharp in all dimensions. And so that we talked about that yesterday. So I'll just kind of skirt over that. Now one of the main ingredients in the proof of this, whether it was proof of the sharp bound for the singular set, or whether it was the optimal regularity for this degenerate elliptic equation, was the uniqueness of cylinders. So this again meant, so in the case of where the initial hypersurface is mean convex, then we know that at a singular time, at a singular point, the blow-up is either a round sphere or a round cylinder. But the problem here is again that the cylinder that you get could depend on, if you take a sequence of rescaling, then a priori you may have to pass to a subsequence to get that is converging to a cylinder. So different converging sequences could lead to different cylinders, right? And so the key for either for the sharp bound on a singular set or for the optimal regularity of this degenerate elliptic equation is to rule out that the blow-ups, so prove that the blow-ups are unique, rule out that they depend on the sequence of blow-up. So this is supposed to be illustrated again in this example here, in this sort of picture here, where right before singularity, if you're looking at the hypersurface and you rescale it, then it looks near the singularity, it looks like this yellow cylinder. If you look at a slightly later time, but still before the singularity, it looks like the blue cylinder. And at even slightly later time, but still before the singularity, it will look like a completely different cylinder, the red cylinder. Right? And so it turned out that this here is impossible. This picture here is impossible. And I will talk a little bit about the proof of this. And then I want to talk about some further results. Some result about other flows, and also some in a way sharpening of this result here, this uniqueness. So in order to do that, let me just be a little bit more precise what I mean by blowing up, right? So we're looking at a flow, and we are trying to. We want to blow up, so we are enlarging, we're rescaling in space, and at the same time we are rescaling in time, and we're doing it in the usual parabolic way because time and space behave differently. And so this leads to a new flow, and this leads to if you do this rescaling, it will lead to the rescaled flow. And for the rescaled flow, it's satisfying a very similar equation. The time derivative of the position vector is given like this. So you get this additional term here. So uniqueness of blow-up is one way of thinking about it is that this flow here, if it has a cylindrical limit, it has but if it has a cylindrical accumulation point, then it has a limit. Right? So this is a way of thinking about it. And so this is kind of a useful way of thinking about it because this introduces also some sort of dynamical system. And so now this flow here, this rescale flow, so this is actually the negative gradient flow. But remember that the mean curvature flow was the negative gradient flow for area or volume. But the rescale flow is actually the negative gradient flow for what's called the Gaussian surface area. So this is the Gaussian surface area was also something that has appeared independently in theoretical computer science. So this is just where you take some Gaussian here, you're integrating it over the surface. So an old result of Quiskin say that this Gaussian surface area is decreasing along the flow. Right? This is essentially that is the negative gradient flow for the Gaussian surface area, the rescale mean curve flow. and so you get this formula here. Right. So now again, fixed points for the rescaled flow. Fixed points, those are stringers. Stringers are just solution to the flow. So if you think about stringers in terms of the rescaled flow, then they're just fixed point for the rescaled flow. If you think about stringers in terms of the original flow, then it means that they evolve by rescaling. So a later time slice is exactly like the earlier, except that it's scaled down. Okay? And so if we just go back here, let me just go back. You see that if it's a fixed point for this, it means obviously that this here is 0. So this means that H satisfy, another way of saying it is that H satisfying this equation here. So this here, so stringer satisfying this elliptic nonlinear equation. Right, and then another way of thinking about stringers, so you can think about it as fixed point for this rescaled flow. You can also think about them as critical points for the Gaussian surface area. Okay, and so right. So now, so now here's some examples of stringers. So this is again, if the initial hypersurface is mean convex, then the only stringers you will see are round shrinking cylinders or round shrinking spheres. But if the initial hypersurface is not mean convex, then there exist others. I think the first rigorously constructed was an example of anchorment of a donut that under the flow, right, evolves by rescaling. So it's a closed, so it's a surface of a donut. There was also example a little bit later, numerical examples. I'll show you a picture of some of those in just a minute, of CHOP and ocean cesium. And there are examples constructed by, now there's also examples constructed by gluing techniques by Capoleos, Klein, and Müller. And they construct an infinite family of these. And there are other examples of Ketover and Shu using min-max techniques. So here are some of these numerical examples from the 90s. And some of these have, it's a little bit hard to say that you have constructed exactly these examples, but it seems like these examples have now been, these are part of this family of examples constructed by Ketover and Su. Right, but there were earlier numerical evidence for them by CHOP. And so this is another example also of CHOP that was numerically constructed. In all dimensions, one know that the only generic shrinkers are, so the only shrinkers that can't be perturbed away are round cylinders or round spheres. And in 3 dimensions, Brendel proved that the only genus 0 shrinkers are the round cylinders or the round spheres. Okay, so there was a little bit about shrinkers in general. Right. But you see also, maybe to say, so most of the time I'll just assume anyway that the initial hypersurface is mean convex, but these results here also justify that the case of where the shrinkers are round cylinders or round spheres, that these theorems here show that these are the most important shrinkers to deal with. Okay, now I want to talk a little bit about the proof of the uniqueness. So what are the ingredients that go into the proof of uniqueness? So there's so it borrows a certain, it really just borrowed the spirit of an idea from real algebraic geometry. And so So now let me try to explain that. So suppose you have a function on Euclidean space, and suppose that you're looking at a flow line for this function. So for the flow line for the gradient flow, for the negative gradient flow of this function. And suppose you have a sequence, right? So eventually, but you might want to forget this for just for the moment. But eventually, this function is going to be like the Gaussian surface area, right? I mean, that's going to be the parallel. But at the moment, let's not even think about that. Let's just think about a function on Euclidean space. Look at a flow line, the negative gradient flow line. And suppose you have a sequence of points tending to infinity, so that these points on the flow line, so corresponding to these TIs, they accumulate towards this point. Right? The question is, so here, right, here's a parallel sort of question about uniqueness. The question is, if this flow line has an accumulation point, does it have a limit? Right? So that's a parallel question. And so, right, and so uniqueness, that it has a limit, would follow if you could prove that the length here of the flow line is finite, right? Then it would follow. And we don't necessarily have this, but this is in general. Of course, I'll just show you an example, just maybe on the next slide. So a priori, what one have is, and this follows from that it's so if you take any function here, then a priori what you have is you don't have this, but you have this here. Just from that is a negative gradient flow. Okay. So now, of course, you're tempted to use Cauchy-Schwarz. The problem is that the interval here is infinite. Right? And so now there's a famous theorem from the late 50s of Lojasiewicz, and it proves this. It proves in a case where you have a function on Euclidean space that is analytic. And it very much, as we'll see in a minute, depends on that the function is analytic. So suppose you have an analytic function, suppose you have an accumulation point, then the claim is that the length here is finite, and therefore we have a limit. Right? This limit here will automatically have to be a critical point, because else it couldn't be an accumulation point. Okay? And so even in R2, for functions, if you have a function on R2, then it's easy to construct smooth examples. So functions that are smooth on R2, that are not analytic, where this uniqueness fail. And so here's a sort of standard example. Maybe the picture is not fantastic, but this is supposed to illustrate the graph of a function. Right? I mean, I admit we got somebody else that was not a mathematician to make the picture for us, and they were really not a mathematician. They didn't completely understand what a graph of a function would look like. So it certainly doesn't look like a graph if you're looking here. But I think you get the idea that imagine that so this is supposed to be right. The picture here is, think about it as an R3. But the function will live on this plane here. This is the graph of the function. And so imagine that you here are on a gradient flow line. If you're on a gradient flow line here, you would have to run down the hill here on this goat track, and you run, but the tracks here they accumulate towards, right, in height they accumulate towards something, but they keep running around the hill, right? And so this is like so it's easy to construct a smooth function where the graph looks like this, where this uniqueness fails.
Sorry.
Yeah. Sorry. If the function, I'm not sure. mean, the functions here we're looking at, it doesn't have any particular nice properties. Okay, so now the key here, so Ricci's theorem was this theorem that said that if you have an analytic function and it has, and you're looking at a gradient flow line, then, and it has an accumulation point, then it has a limit, right? That was the Ricci's theorem. Ricci's theorem was a consequence of the Ricci inequality. So there's actually two Ricci inequality, and it was a consequence of the gradient inequality of Ricci. And so the gradient inequality of Ricci say like this, that suppose you have an analytic function, suppose you have a point x infinity, this is some point, then in a neighborhood of this, there is a constant c and another constant beta. Beta is in this interval, c is obviously positive, so that for all x in this neighborhood, you have this inequality. So the difference in the value of the function is bounded by some constant times the norm of the gradient square. Okay. And so a consequence of this, an immediate consequence of this, gives one of the sort of simple but particular property of analytical function, is that if you take an analytical function and you have a critical point, then in a neighborhood of that, there is no other critical values. Okay? So this is obviously, you can obviously, for smooth function, this also fails. And so this here, if you have this kind of inequality, then it actually leads to a rate of decay for the value of the function as you are traveling along this gradient flow line, and this gives you, by some simple integration by parts argument, this gives you that this here, it gives you a bound for this integral here, showing that the length of the path is finite. Okay, and so this is what gives uniqueness, right? So in order to prove uniqueness, if you can establish this kind of inequality, you're in very good shape. Okay. Now, there's a second inequality of Lojasiewicz, just to give you a little bit idea of the history of this, and then it will connect to something later on. So there's a second inequality of Lojasiewicz, which is usually called the first Lojasiewicz inequality. And it's again you're dealing with an analytical function on an open set of a subset of Euclidean space, and you're looking at the zero set of this function, and then the claim is that the distance to the zero set is bounded in terms of the value of the function, right? And so this is also, of course, a property that is very particular for analytical function. And so these two Lojasiewicz inequality are closely related. Here, right, alpha and c are allowed to depend on the function. Okay, so now, again, just to give you a little bit of idea of the history of this, so Lojasiewicz used this inequality, so he used the first inequality to prove something that was an open problem at a time, which was Laurent-Schwartz division conjecture. Hermander proved at almost the same time. He proved independently Schwartz division conjecture, but only in the special case of polynomials. And also in Hermander's case, the key step was this Lojasiewicz inequality, but he could only prove it for polynomials, whereas Lojasiewicz could prove it for all analytical functions. Okay, a little bit later, Lojasiewicz used his second inequality to prove a conjecture of Whitney. Whitney conjecture said that if you have an analytic function on an open set, then the zero set of this function is a deformation retract of a neighborhood. Okay. Right, and so the main tool for us is, and it's just this loose idea, because it actually has nothing to do with the proof have nothing to do with the proof of this Lojasiewicz inequality. Our functions are also not analytical, but it's just this idea that if you have a certain inequality, then you are in good shape. Okay, and so our inequality will be for this infinite dimensional functional, which is basically the Gaussian surface area on the space of hypersurface. Right? And here the really big difficulty is that the hypersurfaces are non-compact. I mean, that's a crucial point. That's why we cannot reduce it. I'll talk a little bit about this later, to the classical Lojasiewicz inequality. And to some extent, sometimes one are allowed to be a little bit lucky because we, in a way, stumble upon this. We proved something, then we thought more about it, and we thought that this must be a special case of a Lojasiewicz inequality. I'll talk a little bit about that later. Okay. But the whole idea about that uniqueness would follow from that uniqueness would follow from a kind of Lojasiewicz inequality was pioneered by Leon Simon. In Leon Simon's case, he could reduce it to prove to actually the classical Lojasiewicz inequality. So in Leon Simon's case, so he proved a Lojasiewicz inequality for hypersurfaces, but it was for closed hypersurfaces. And so in that case, you can write the hypersurface as a graph over this critical point. And for the area functional, you can write it as a graph over the critical points. And you only need to worry about where the graph is, where the function that gives you the graph is correspond to low eigenvalue of some compact operator, right? And so this actually reduces it to a question about a Lojasiewicz inequality for a finite dimensional Euclidean space, and then you can apply the classical Lojasiewicz theorem. Okay. The problem is we can't do anything like this here. Okay, and so Felix Schulze, he proved in a case where the shrinker is compact, then he used Leon Simon's approach to prove uniqueness. Right, but again, for us, the problem here is that the singularities are compact, so we can't use any of this. Now, part of what we prove is that the proof of the uniqueness. So the proof of uniqueness is actually very general. It's saying that right. I'll come back to that a little bit more. But one of the things we have to prove is that we get convergence over these expanding regions. So as you are going down towards a singularity, we're proving that the region where the hypersurface after you rescale it to unit size is getting larger and larger at a definite rate, a specific rate that we can estimate. Right. And so in this sense, we have information that sort of propagate out, so it becomes larger and larger. So it's information that from a compact set is propagating out further and further out as we're going in. And so now remember that there was a consequence of the Lojasiewicz inequality was that if you take an analytic function on Euclidean space and you're looking at it's only right, so and you're looking at a critical point, then in a neighborhood of that critical point, the function has no other critical values, right? And so this theorem here is a kind of analog of this. And so we proved this earlier than uniqueness. We proved it together. Bill and I proved this together with Tom Illman. And so we proved that if you take a shrinker that is sufficiently close to a round cylinder on a large, I just mean a large ball centered at the origin, so large compact ball, then it must itself be a round cylinder. So you can kind of completely, but I mean, you just know a finite piece of the surface, and then you actually would know the rest, right? And so, right, so you can think about this theorem here as a special case, as a consequence of a kind of Lojasiewicz inequality.
One has some global information.
That's right. One has some global information.
The Gaussian area.
Exactly. That's right. Yeah. Right. Right, but that's a very weak. That's a very weak thing that is given. I didn't. Right. That you get to assume. Okay. Right, and so the proof of this proves Lojasiewicz proof. It goes over proving two kind of Lojasiewicz inequality. But again, the proof go very differently. They are done directly here. And so the first Lojasiewicz inequality we proved. So here, F here is this infinite dimensional functional, which is this Gaussian surface area, and C here is a space of cylinders, which are these critical points for the Gaussian surface area. And we are saying that the distance from a hypersurface to one of these critical points for this infinite dimensional functional is this distance squared is bounded by some constant times the gradient of this. Right?
So distance is what exactly?
Distance is like a Gaussian distance. Yeah. But it's I'm not being super precise, so I want to warn you here. Right? So, and we essentially get not quite, but we essentially get. I mean, for various reasons, including various interpolation arguments, that we don't get to. I mean, you don't need to have a sharp, but we essentially get the sharp dimension, right? The power there. And so one of the other key difficulty here in proving this is right. So of course, when you're trying to prove that the cylinder is unique blow up, well, of course you're dealing with that the cylinder could a priori rotate, right? So this corresponds to Jacobi fields, but there's another Jacobi field. There's also other Jacobi field. There's a Jacobi field that is so if you go back to this statement here, that was the wrong way. Sorry. If you go back to this theorem with Thom here, so we proved that cylinders here are rigid in this strong sense where you just have information about a compact piece. They are not actually infinitesimal rigid. So there is actually a Jacobi field here on a cylinder, but this Jacobi field, it of course exists all the way out to infinity. It's not actually integrable, okay? But this causes a big headache, okay? So this is a big headache. Existence of Jacobi fields is kind of a well-known thing. again, there was this. There was another approach to uniqueness around the time of Leon Simon. It predated actually Leon Simon with a couple of years of Allen and Almgren. I mentioned this yesterday. And in their case, they assumed that they were dealing with something that was integrable. So they got away with that. Then the argument became much simpler. Okay.
Is it clear where this what it corresponds to?
It's kind of hard to say what it corresponds to because it's not integral. No, it's not a rotation. Yep. Okay, so right. Okay, so now right. Okay, so again, so we're proving this by reproving. This here was the second Lojasiewicz inequality. Sorry, right. So we talked about this here was the analog of the first. Right, I'm just stating them roughly. Right. I have some slides later on that I will skip, where it's stated much more precisely, but you don't want to see that. And so here, this is like the rough version of the gradient Lojasiewicz inequality for this infinite dimensional function. C here is again the space of cylinders. Okay, and so now using this gradient Lojasiewicz inequality, then we get a rate of decay along this flow line. We get a rate of decay for f, and this then implies that the distance traveled here is finite, and this gives you uniqueness. Okay. Okay. So now, right. So again, but we talked about this now a bit, but it's important here to note that you don't actually. I mean, these Lojasiewicz inequality are proven directly. They have nothing to do with trying to reduce it to Lojasiewicz argument or to cases where a Lojasiewicz inequality would be known to hold. Okay. Right. And sorry. Yeah.
Implied with finite dimensional inequality at special case. So is it good to
the finite dimensional? No, it doesn't. No, it doesn't. But I'll talk about that. I'm going to skip a bunch of stuff now because I every day here I've been way too optimistic with what I could cover. So I'll skip a bunch of stuff, and then we will get to something sort of related to this. Okay, so this is some stuff that go into the proof. I'll skip all of that. Yeah, sorry about that. So you see this kind of. Okay, so now I want to turn to something else. Right? So we're dealing here with so now I want to return to this degenerate elliptic equation that we were looking at yesterday. So this is the level set equation for the mean curvature flow, right? And so so in the case where the initial hypersurface is being convex. So I now return to this degenerate elliptic equation where yesterday we talked about optimal regularity for this. But again, just to remind you, optimal regularity was that the function was always twice differentiable, but the second derivative, but the second derivative was not always continuous, and there was also this result that even when the second derivative is continuous, it may not be C3. Okay. So now, if you're looking at sort of very classically, if you have a elliptic PDE with analytic coefficients, then the solutions are analytic, right? So this is a kind of simple classical result. Degenerate equations, as we've seen, have much lower regularity, and solutions are typically only defined in a viscosity sense. Now, if we're looking at the arrival time function, So this is this function that again satisfying this elliptic equation. So the hope here is that and so I mentioned this before. The hope here is that even though the function has very low regularity, the hope is still that it behaves like an analytical function. And I'll try to give some evidence now for that. So now for the arrival time function, we can prove a Ricci inequality. So this is now the arrival time function is now a function defined on a finite dimensional Euclidean space, right? It has, so here I'm assuming it's C2, right? So if it's C2, using this infinite dimension, right? So if it's C2, then we can prove this Lojasiewicz inequality. This is the gradient Lojasiewicz inequality. Right, and so in particular, of course, for the arrival time function, once you have the gradient Lojasiewicz inequality, you automatically get the conclusion of Lojasiewicz theorem, namely that namely that if you have a limit point for a flow line, then it has a unique limit. Right? Now, around so Rene Thom in the late 60s, early 70s, worked in singularity theory. And so he was interested in a generalization of the Lojasiewicz theorem, the gradient Lojasiewicz inequality. And so Rene Thom conjectured that if you take a flow line if you're looking at an analytical function, and you're taking a flow line, and then the secant has, so this is a sharpening of Lojasiewicz theorem, right? So it assumed Lojasiewicz theorem, and then which was known, of course, at that time for analytic function, but then it asking for that not only do the flow line converge, but the secant converge. So by the secant, I mean that if you so imagine that you have a curve that is converging at infinity, converging towards this point. If you're looking at the secants, so these are the secants, right? And then where you rescale these to unit size, then they converge. Okay, that's a secant, right? So you're looking at not only does this distance go to 0, but if you rescale it to unit size, then right, it's like yeah, exactly. And so this, of course, is the picture that you want to rule out, right? So, and again, this conjecture arose in Thom's work on singularities theorem. And so this here is supposed to show, exactly like Vitaly is saying, that it can't spiral kind of in towards this. This here is like the critical set of this function, right? Again, Thom's conjecture is that this figure here is not possible. And so we can prove, and it actually is, it's pretty non-trivial. But we can prove. So I should say that Rene Thom's gradient conjecture was proven for an analytical function in 2000 by 3 Polish guys, and we can prove for solutions to this degenerate, so C2 solution, remember that C2 solution may not be C3. For C2 solution to this degenerate elliptic equation, we can indeed prove, for this degenerate equation, we can indeed prove Thom's conjecture. In fact, we can prove a stronger conjecture that implies Rene Thom's conjecture. This was a conjecture of Arnold. Rene Thom was giving lectures on singularities theory and talked about it in Paris in, I believe, 72, and was talking about his conjectured improvement of Lojasiewicz inequality. And then Arnold came up with this improvement, which is still open for analytical function, but in this case, we can actually prove also the Arnold conjecture. Now, in the last few minutes I have left, I want to talk a little bit about other equations. So what about other equations? Are these techniques useful for other equations? Yeah, sorry. Right. You see, no, it doesn't. I mean, the proof of this, the proof here is it actually it go over proving an improvement of the uniqueness of Lorentz. Okay, it's kind of right. I mean, so you see this here, that is so. No, that's right. Yeah.
Without mean curvature, can you coordinate these arrival times?
Right. I mean, you can. I mean, I mean, you know, there's this parabolic. I mean, so the level set equation right now is like this parabolic equation is on a more elliptic equation, and there should be some version of it. I'm not 100% sure what the version of this here is. I haven't really thought about it too much because.
So the level set only makes sense because of
the level set, right? I mean, the arrival time. Yeah. I mean, the level set does make sense fine, right? I mean, because you have in the general case, if you're not assuming mean convexity, then you have a function here defined on Euclidean space cross time go into R, and then what you're looking at is that T go into, so you fix S, and then you're looking at T go into U inverse T, no, sorry, U the pre-image, it's the pre-image, maybe I should write it like this, it'll get too complicated. So T go into the pre-image, the X in Rn plus 1, where U X comma T is equal to that S. So for each S, these level sets here are flowing by the mean curvature flow. That gives you the parabolic version of the arrival time equation. Okay, and so okay, so now I want to talk about further development. So what about other equations? Are these techniques useful for other equations? Oops, I'm not sure what. In particular, what about system of equation? And so, Ricci flow, right, that's a system. The unknown is the metric. So the metric is evolving by this equation here. And shrinking solitons, again, so for this equation here, shrinking solitons are the singularity models. By result of Hamilton, Ivy, Perman, Ni and Wallach, and these other, and Chow, Chen, and Su, in 2 and 3 dimensions, shrinking solitons are spheres and round cylinders. In higher dimensions, there are many other examples. Okay. Now, it's expected that in all dimensions, the most prevalent singularities are cylinders, so cylinders of this form here. The second most prevalent singularities are also cylinders of this form, right? And this, when I'm talking about prevalent, then I'm thinking about in terms of stratification of the singular set. So these are the ones that have the largest there's the largest measure. Okay. Now, so this is work so now I'm actually getting a little bit, but I'll finish a little bit earlier then, because now I've skipped so much. So this is work in progress, but so we think we can prove this. I mean, we have actually written this one down. So this here we can prove, and this is the analog of this result that we did earlier with Thom Ilmanen. So if you take a shrinker for the Ricci flow, then it's isolated in the space of cylinders, which means that if you take any other shrinker that is close to that cylinder, it's close on a compact set, large but compact set, then it must actually be a cylinder, okay? And so this is the analog of this. We think we can also, but that's very much work in progress, we think we can also prove the corresponding uniqueness of blow-ups in this case. And so again, so I think I'll just finish with that. So thanks very much.
Question?
This picture of the level set.
Yeah.
The general elliptic equation.
Right.
Not general. Inverse curvature flow.
Right. That's right. That's right. Yeah.
How general is this? So in curvature flow, you can reduce it to a general elliptic equation.
Yeah.
Inverse curvature flow. It's just an elliptic equation.
Right. That's right. That's because you usually also, but I mean, because you're kind of assuming that it's also in convection.
How general?
I mean, it's very general again. I mean, so the level set method. So two things. One is that most of these results, all of this with uniqueness of blow up. This is just assuming that it's a cylinder. Mean curvature positive doesn't play any role in the proof. Okay, and the same here. There's no curvature restriction in this case of Ricci flow. Right? So that's one comment. Now I lost track of the second comment I was going to say. You say how.
By distance.
Oh yeah. So that's right. So again, so it's quite general. I mean, so there's this. I mean, if you look at these, all the numerical work, right? For the level set methods, then there's within that there's a very large subject of techniques. So there's this extremely well-known numerical method called the fast marching method, and that is giving a very efficient way of numerically treating the case where the flow is moving in just one direction.
So for the Thom conjecture, how does it mean geometrically?
Yeah, that's a good question, and that's a good question. It's a little bit. It's not totally clear. That's right. That's right. That's right. I mean, it's right. It's a good question. I mean, the thing is, and maybe that to some extent answer it, that we prove a nearly sharp rate. I mean, to some extent it probably answers it, because, to prove this Rene Thom and the stronger analytic conjecture, we prove a nearly sharp rate for the convergence, right? And so you can see that, if that it avoids spiraling is kind of closely related to giving a better rate, right? And so that's why you have to work, actually, even when you have uniqueness, you have to work quite a lot.
I have a more elementary question.
Maybe I'll say one thing to you still. I want to just point out there was something that came up yesterday, and I think it's still. I just want to point out that we don't know this, but I think it's a very interesting question. So in the case of this Rene Thom conjecture, we can only prove it when the function is C2, right? And the starting point for Rene Thom, remember the Rene Thom conjecture it was really a conjecture for analytical function, also the Arnold, right? So C2 is not too bad here. It's still very reasonable to ask, does it hold, even in a general case where we just know it's twice differentiable? And we don't know that. We don't know whether that's true. In fact, we don't know whether you have this inequality and this exactly, and that was related to that question that came up yesterday, right? So a consequence would give you an answer to that. Yeah. Sorry.
Yeah, more elementary question. Like when you study PDE, maybe there's that maximum principle.
Right. Yeah. I mean, so the maximum principle here, it came in, but it's not. It came in the very beginning with the avoidance principle, right? And so that you have this shortened hypersurface, but it doesn't really play very much role in all of these proofs. I mean, it doesn't actually figure in for many reasons, including that the objects are non-compact, etc., etc.
If not, yes. Thanks for